Hello again. Welcome in week number 10. I'd like to cover deadlocks, which I will continue week number 11 as well. So, what is about deadlocks? We will cover the problem and define a problem of deadlocks. I will cover two ways of system modeling. Then some characteristic of deadlock, methods of handling deadlock, including ignoring deadlocks as well, how to prevent, how to avoid, and how to detect, and then how to recover from deadlock. So we will describe the deadlock, which allow to prevent concurrent processes from getting stuck and from completing the task. And we have several methods for preventing, avoiding in computer system. So the two processes are deadlock if they occupy certain resources and require another resource which is currently occupied by second process, which requires back the process of the first, the resource of the first process, which is currently being used. So if we start using semaphores, you may remember that whenever a process is executing the wait function, p function, on semaphore A, the semaphore becomes 0. So if two processes are using their semaphores to control their own resources, if they both come at the same time and execute the entrance function wait, they make the semaphore to be 0. And obviously, if the semaphore is 0, another wait function cannot be executed. So let's have an example, narrow bridge crossing example, in which we have two cars occupying those narrow areas. Each is occupying its own resource. So car P0 is occupying its own resource R0. P1 is occupying its own resource R1, and they claim each other's resource, so they get stuck. Please notice that every of those resources, resource R0 and resource R1, are somehow controlled by the semaphores. P0 controlled by semaphore A, B0 controlled, R1 is controlled by semaphore B. So when those two cars, two processes enter their resources, of course, the semaphore is closing behind. Now, in order to for other cars to enter, they have to be set to 1. By they cannot advance. So we have traffic in only one direction. Section of the each section of the bridge obviously is viewed as a resource, as you can see on the picture. If deadlock occurs, the only solution would be to back up, which we call preemption. So it may happen that several cars may have to be backed up. So the starvation is possible, which means such situation may last infinitely. To use a more formal description, you can see that P0 is executing PS, then it wants to execute P of Q, and down in the table, in the same direction, they want to execute signal functions V of S, V of Q. P1 in the second column does execute its wait function P of Q and wants to execute P of S to enter to another resource, right? And then when they leave their own resources, they execute the signal functions, V of Q and V of S. So deadlock is a condition where no process can proceed its execution because they occupy resource which is claimed by the other process and vice versa. Starvation, which means is continuous blocking of using the resource, preventing low priority process to require such a resource. Graphically, you may see on the left bottom picture that we have two processes, P0 and P1, and we have two resources, and they are assigned and require their resources and vice versa. On the right hand side, you have case of three resources, but in more details, let's continue. In the system model, we have resources, M resources from R1 to Rm, and resources may be any CPU, memory, input-output devices. Each resource may have several instances. We may have obviously many input-output devices. We may have also many CPUs. Each process, while utilizing the resource, may request the resource, may use the resource A, and may release the resource. What are the conditions for the deadlock? So we have four conditions which are necessary conditions to make a deadlock. We have to have mutual exclusion. So only one process at a time can use one resource. Hold and wait. So the process is using a resource while waiting to acquire another resource which is held by another process. No preemption. We can have preemption, but if we satisfy the preemption, this is the third condition for having a deadlock. So the resource may be released only by the process itself. And then we have circular wait. So the processes from P0 to PM are requiring next and next resource, which are held by the next and next process. Graphically, it will look more evident. So when we create a graph of resource allocation, such a system, we have vertices V and we have edges E. V is partitioned into two types. So they may be the processes and they may be the resources. The edges, such like arrows, which signify the request edge, it's the edge and the arrow from process to the resource. Assignment, which means the process is using currently the resource, it's an arrow from resource to the process. Just on the contrary. So the processes will be represented by circles, resources by squares, with inside small squares representing the instances. So when we have the situation, the process PI is requesting instance of Rj, it's an arrow from PI to Rj. And if P process is holding, the arrow goes from a certain instance of R to PI. Let's have an example of such a resource allocation graph. We have three processes. We have four resources. Resource 4 is not being used. Resource 2 has two instances, and P1 is requesting R1 while being assigned one instance of R2. P2 is requesting R3, but is assigned two other resources, R1 and one instance of R2. Here with an example of the graph, resource allocation graph with a deadlock, because we have a circular relation between processes P1, P2, and P3. We may have the allocation graph with such a circular situation, but there is no deadlock, because in this case we have two instances, and processes P2 and P4 may release its instances of resources R1 and R2, therefore allowing the processes, remaining processes, to get what they want. So let's have an example again, and let's get back to the situation on I will increase a little bit. So let's have the situation of the narrow street or bridge situation, and we have a deadlock if P1 occupies its resource R1 and P2 occupies its R2, and at the same time P1 is requesting R2 and P2 vice versa requires R1. So we have evident circular relation between those processes and resources. How to recover? Well, one of the possibility is P1 releases R1. Okay, so this arrow from P1 to from R1 to P1 disappears, and this is beginning of the solution of the problem. If you want to prevent, we have to allow process P1 to use R1 and then R2. Once it is done, the P2 is coming and doing the same in opposite direction. You have here several examples of resource allocation graphs for different street crossing situations, to which we will return later on. We have example of two street crossing with 4 resources and 4 processes. It may happen that if all of them are assigned all those resources, that is obvious a deadlock, and the starvation is possible. So this is a deadlock when we have a circular relation between those processes and resources. Another situation which is not a deadlock situation is a one-way street and no lights, and cars advance straight ahead, therefore there is no deadlock. The P1 is assigned R1 and then can leave the resource R1, then P2 can be assigned R2 and then go ahead and leaving R2 to P3. When you have the crossing with lights, we separate parallel and vertical circulation into two. So first, the horizontally green lights are on, therefore the horizontal cars can pass the crossing. Then when we change the lights, the vertical, the street is activated, and independently from the horizontal one, they can pass and get their own resources. Once we are done with notions of deadlock avoidance, prevention, and recovery, we will get back to those models of street crossing. Interesting is roundabout, because you remember the roundabout is avoiding deadlocks. So if the graph is containing no cycles, no deadlock. If the graph contains a cycle and we have only one instance per resource, then we have deadlock. If we have several instances, possibility of deadlock, but the deadlock is not necessary, as you remember. How do we handle the deadlocks? So we can ensure first that they never enter the deadlock state. So this is kind of prevention. And then when we have the deadlock, the question is how to recover. Interestingly, we can also ignore the problem of deadlocks. Certain operating systems assume the deadlock never occur, and one of those systems, surprisingly, is Unix. What they say that checking and running the algorithm of preventing and then recovering is so time consuming that maybe ignoring is better, because once we have a system crash, recovering from the crash does not happen very often. Such deadlock situation does not happen very often because it's not very common that several processes arrive and request the resource exactly at the same time. So because of certain statistical calculations, they came to the conclusion that it is better to get out from the crash than running every time, running those algorithms of preventing or recovering. What's happening when we want to prevent? So we have to restrain. We have to come to the situation that one of those necessary conditions is not satisfied. Mutual exclusion, well, it's not required when we have shareable, but must hold in a non-shareable. So there's not much freedom here. Hold and wait. So must guarantee that whenever a process requests the resource, it does not hold any other resource. So the process before requesting the resource must release its resource. So the problem of this solution is low resource utilization, and start derivation is still possible. No preemption. So if the process is holding resource, cannot immediately allocate another. So all resources currently being held are released. So preempted resources are added to the list, waiting list of resources. Process restart when it can regain its old resource. Circular wait, there is one interesting method that the resources are set in certain increasing order of enumeration. So there is a method. To avoid, we have to have certain additional a priori information. So the process must declare maximum number of resources. So deadlock avoidance will cover in a moment in more details in the Banker's algorithm. So deadlock dynamically avoidance examines the resource allocation and prevents being in a circular and wait condition. So we have to have a defined number of available and allocated resources. It requires certain calculations. So the process may be in safe state or maybe in not safe state. So if we know that the situation may be resolved without deadlock, the state is called safe, okay? So the system is safe if there exists safe sequence of all processes without deadlock. You will see in details in the banking algorithm. So if the system is in safe state, not deadlock for sure. If the system is unsafe, there is possibility of deadlock. So avoidance means we never enter into unsafe state. So after having this information, you can get back to slide 1418, create the models and find out what is possible to do to avoid and to recover from the deadlock. So graphically, we have two big states, unsafe and safe. In safe state, there is no possibility of deadlock. In unsafe, we may have, but we don't have to have the deadlock. Let's have this Banker's algorithm. We have multiple instances of the resources. The process must know the maximum claim of resources, whatever the process may claim, maximum. So when the process is requesting, it may have to wait a little bit. And when the process gets all the resources, it must return them in a finite amount of time, of course. So let's take a look on the methods of deadlock avoidance, the Banker's algorithm. I will increase a little bit. So what we have resource vector R. So every process out of M of them has certain amount of resources. Availability vector V, those are the resources which have not been allocated to a process. Claim a matrix, this is what the resources may claim. So every process has its own resource they may claim at maximum. After the processes are claimed, obviously they've been allocated. So again, every process has a certain number of M resources which are already allocated. There are certain rules, relations between those elements of those vectors. The totally number of resources, it's whatever is available plus what is allocated, okay, to certain I process. Whatever is available is a difference between all existing resources minus what has been allocated. Then the process cannot claim more than there is resources assigned to a certain process. And obviously the number of allocated cannot exceed the number of those which the process claimed. So the relation, double relation, inequality between those elements is the allocation of certain resource for certain process is less than whatever the process can claim, and all of them are less than all existing resources for certain specific process. So let's have the situation here. Let's have three tables. The leftmost table says how many resources out of three can exist for four processes. In the middle, you have the table of allocation. How many of all three resources have been already allocated? On the bottom in green, you have the sum of all allocated. So we have total resources is 936, allocated is 925. So we have certain freedom of action. So the second and third resource is still available, while the first one is not. And now available is a difference between C and A, and we know that process 2 has 0 available resource 1, 0 available resource 2, and 1 of available resource 3. So we have total availability of resources is R minus A, therefore 0, 1, 1, which means there is no resource R1 available. So if the process is asking for resource 1, it cannot go ahead. So P1 may potentially claim 2 and 2 and 2, so there's not enough because it's at every component is bigger than whatever is available, which is 0, 1, 1. We cannot touch P1. P2 may potentially claim 0, 0, 1, so may not claim R1, R2, but may claim one of resource 3, which is okay. In the conclusion, we say we can start P2. Once we start P2, we change the situation in those three tables. P2 is done. We exclude it from the table at all. And now available vector is 3, 2, 6. So any process, because we have 6 resources, 1, 2 resources, 2, 3 resources, 3, none of those processes would claim more. So claim is less than V for each resource. So any process can start up. So if we continue with P1, we eliminate P1, the number of available resources is increasing, it is 713, and every process may go ahead. So we can continue with P3, and then we can continue with P4, and we avoid a blockage. If we change the situation and we have a limited more allocated, so P1 has allocated 2 R1 and 1 R3, so we have 0 R1. Therefore, we have the situation of a not safe state, because if the process requires R1, it is 0. So obviously we have to avoid this requirement. But it's not the deadlock. We can run P2 instead of P1. A couple of words about recovery. So we have a couple of possibilities to recover from deadlock. We may make a very dramatic decision and abort all deadlocked processes. We can abort one process at a time until the deadlock cycle is eliminated. And the question is, we have to choose the victim, okay? Which ones to eliminate. So in which order to choose? First of all, we can refer to priority. Less priority, lower priority would disqualify process to be eliminated. Then time of computing. Okay? If the time is short, go ahead. The number of resources, if the system is, if the process is requiring less resources, go ahead. How many resources the process needs to complete? If less, go ahead. How many processes will need to be terminated? Okay, so we select the correct one. Is the protect interactive or batch interactive require more other processes, so batch is better to be selected. So recovery from a deadlock, if we decide to preempt, selecting a victim, which means minimizing the cost, okay, time and resource cost. Rollback, return to certain safe state and restart the process for that state. Starvation, some processes may be always picked as a victim. Okay, include the number of rollbacks in the cost and cost factor, of course. In a summary, you have deadlock detection, prevention, and avoidance approach by the system. And you may see that in prevention, we have here different scams, okay? Preemption, resource ordering, requesting all resources with their major disadvantages. So, for instance, resource preemption may preempt more than necessary, and then may be subject of requested cycling. And so avoidance, okay, midway between the detection and prevention. And the disadvantage is future resource requirement must be known. And this is what we have in Banker's algorithm. And the processes can be blocked for long periods because waiting for other processes. Thank you very much, and see you in the week number 11.